Now let's take the limit of this as L is much bigger than R. If L is much, much bigger than R, what would this come out? Okay. Well, the length will dominate the radius, right? So the magnetic field will approximately equal what? Mu 0 Ni over 2. And then this will be dominated, so you'll have L squared over 4 to the 1/2. Mu 0 Ni over 2. The square root of L squared over 4, L over 2. 2 and the 2 cancel. Mu 0 Ni over L. This is beautiful. Awesome. This is exactly the approximate equation we get. Magnetic field is equal to mu 0 Ni over L. So that's exactly the equation we get when we use Ampere's law, making the assumption that the magnetic field in a solenoid is uniform, and we do a little loop around the inside of the solenoid and the outside of the solenoid, and we get the approximate same equation. What would be the magnetic field at the edge, at the front edge of the solenoid? Okay? Right here and right here. So then what we do is we put D is equal to 0, right? D is equal to 0 into our general equation. Okay? So let's see what we get there. D is equal to 0 because I'm at the edge of the solenoid. Okay, so D is 0, this disappears, of course, that's gone. This is 0, this is 0. And now L and L cancel. So what do you end up getting? You get mu 0 Ni over 2. The L cancels with this L. This D disappears. I'm left with R squared plus L squared to the 1/2. You got, this one is 2. This one, remember the other one had L squared over 4 here. Okay? So now let's take the limit of this as L goes much bigger than R. L is much, much bigger than R. So what happens to this? Mu 0 Ni over 2. Again, the L dominates the R, so it just ends up getting L squared square root. So this thing disappears. Now it ends up getting L. So basically this means that the magnetic field is approximately equal to mu 0 little n I over 2. So the magnetic field at the edge of the solenoid, if it's long enough, can be approximated to be about half of the magnetic field at the center of the solenoid. Okay, so that's an approximate approximation, because it's the difference of this equation and the general equation for the center of the solenoid was mu 0 Ni over 2 R squared plus L squared over 4 to the 1/2. So because the biggest difference was that this one was L squared, this one was L squared over 4. So when L is much bigger than R, this became L over 2, which canceled with that. And then this one just stayed as L, so the 2 ended up remaining. So an approximate equation is that when the solenoid is long enough, the magnetic field at the edges are half the magnetic field at the center. Essentially what that means is that when the solenoid is like this, long, at the center the magnetic field is pretty uniform, so pretty straight, and it's strong. By the time you get to the edges, the magnetic field starts coming out, starts diverging, okay, like this. So the magnetic field concentration at the edges is about half as much as the magnetic field concentration at the center. So because of the divergence of the magnetic field. Okay? By the way, you could also use this equation to generalize the magnetic field at the ends of a magnet. So imagine a magnet, south-north. Essentially, what is a magnet? A magnet is like a solenoid. Okay? Goes like this, like this, like this, like this, like this. So imagine the length of the magnet. Imagine the radius of the magnet, R. So that'll be the radius of the magnet. So here's what we'll do. Magnetic moment of a coil is equal to NIA. number of terms times the current times the area. So that would be Ni pi r squared. So you see, when you see Ni, you could replace it by mu over pi r squared. So the magnetic field of a magnet at the edges here, the two edges, is going to be mu 0. Ni is going to be replaced by magnetic moment over the two stays there, pi r squared plus L squared to the 1/2. So this could be the general equation for the magnetic field of a magnet. Mu 0 is the magnetic permeability, magnetic moment of the magnet. R is the radius of the magnet, so it's basically half the width of the magnet. The radius squared plus L squared. If the length is much, much longer than the radius of the magnet, then you could be mu 0 mu over 2 pi r squared, and the length dominates again, so it becomes L squared square rooted, so it just becomes L. So this becomes an approximate equation for a long magnet. It's a very good example, this one, that you could use to calculate the magnetic field of solenoid. Anywhere from the solenoid, you could approximate for at the edges of the solenoid, the middle of the solenoid, and for a long solenoid, and then generalize it to any magnet, and then find the magnetic field at the edges. You could also find the magnetic field anywhere along the axis of the magnet, so just generalize it to some other point. Thank you very much.